Hello, this is Guillermo Campitelli, and in this video I'm going to show you how to do how to apply the 7 approaches to a case in which we have only one numerical variable. So in this case study, it's a study in which we have a sample of 400 participants and we took an IQ test. So we've got 400 values in IQ, so that's all we have, only one variable, and let's see what we can do with just this. Okay, so let's first show you the descriptive statistics, and here you've got the instructions. I'm going to bring JASP and carry out that. So basically, first of all, we need to get the file. You go to File, and if you use it recently, it will be there. Otherwise, you if it's in your computer, you press here and you browse over there. So I just return to recent, and I get it there. So it's open like this, so I'm going to just close one of them. Okay, so first we want some descriptives, so we go to descriptives, descriptive statistics, and we drag intelligence into the variables box, and we can display frequency tables. Sorry, this we don't need because that's only for nominal and ordinal variables. So we've got here mean, standard deviation, minimum value, maximum value, if there is any missing and non-missing. And we've got plots. We can have a distribution plot, which looks like this. And so we've got this plot. You can also, if you go there, you can increase the size of the figure. So that's the distribution of your data, and return to, you click there to return to the place where you can put your preferences. Now we want a box plot, and this will appear here. So this is the box plot of your data in intelligence. I like the violin plot, so we put the violin element. So now you've got the two, they don't look good, so you either have the violin or the box plot, not both. So that's the violin that shows you the distribution. So basically here where the violin is fat, it means that you've got most of the you've got a lot of values over there, and where it's thinner there are very few values. And the jitter element, basically it shows you the whole data, and obviously it doesn't look very good. So I'm going to see if by increasing the size. So if you get this thing in the corner, you can increase the size. So sometimes doesn't look good. In that case, I would just either present just the raw data, or the violin element, or the box plot. Okay, in terms of statistics, you can tick there and get things you want. So basically, standard error of the mean is technically not descriptive statistics, because you use the standard error of the mean when you do parameter estimation. So if you tick there, it will appear in the table here. So your standard error of the mean is here. And if you want quartiles, percentiles, or cut this sample into 4 equal groups, the median, the mode, the sum. skewness, kurtosis, variance, and range you can also add. Okay, so basically that's the descriptive statistics that you can do with JASP. And here I did these graphs with R. I did the same thing. The violin plot looks a bit better there because I changed the size of the dots. And here is the distribution, the histogram with the mean as vertical bar. Now remember, in JASP you can always select, copy, and you go to Word, you put it there, and you've got the graph ready for publication. Okay, so let's start with parameter estimation. Let's first show you the traditional frequentist approach, then the Bayesian, and then resampling. So we use JASP, and basically what we do is we use the descriptives and we put the standard error of the mean, we tick that, we calculate by hand the 95% confidence interval. So basically we go to JASP and standard error of the mean, and here 0.582. So basically what is easily the 95% confidence interval is the mean minus 1.96 times the standard error of the mean. So 110.56 minus 1.96 times 0.582, and that's 109.42. And the upper bound of the 95% confidence interval is the mean plus 1.96 times the standard error of the mean, and that's 111.7. Okay, so that's the confidence interval for the mean of IQ. Okay, so that's the parameter estimation. Now let's do Bayesian parameter estimation. We need to use software. Remember that the software typically are good at doing things with which we study the effect of one variable on another, not just one variable. So parameter estimation on one variable only is not that easy to find in software. You have to find tricks. Okay, so I did it with R, and basically you need to find define a prior for the mu of intelligence. So what's the mean of intelligence in the population that we obtain our sample from? Okay, in this case the prior distribution is a uniform distribution that goes from 70 to 130. So basically because we've got the knowledge that population with mean of IQ of 70 or lower than 70, it's impossible, and a population with a mean larger than 130, it's also impossible. So unless we have a special populations with people with cognitive disabilities or gifted people, but because we obtain randomly from the general population, is very unlikely that it would be smaller than 70 or larger than 130. So instead of putting as prior a uniform over all the possible values of the mean of IQ, we restrict that, and that gives us a bit more power in the analysis. So then we need a probability distribution to determine the probability of obtaining each possible score in our sample. So that's we use a sampling distribution. So in that distribution, the mean is each possible value of mu, so from 70 to 130, and the standard deviation I fix it to 1. That it's not compulsory. I can put a prior on the standard deviation and let the software estimate the standard deviation. But because we are not so interested in the standard deviation, I set it to 1. And basically we've got a probability distribution for obtaining each value of the each possible value of the mean in our sample, given each possible value of mu between 30 and 70, weighted by the prior. But in this case, between 30 and 70, the prior is 1, so we would have the same weight. Now, when we've got that distribution, we observe what's the actual data. So in our case is 110.56 is the mean we observed in our sample. So we use all the probabilities that we had for that value, 110.56. So if the parameter was 30, how likely is to obtain 110.56? If the parameter the value is 40, how likely is to obtain 140? Sorry, I should have said not 30 or 40. Start with 70. If the mean is 70 of the population, how likely is to obtain a mean of 110? If it is 80, if it is 90, 100, how likely is to obtain this mean in our sample? And that's here. When we use that, so if the parameter of the population is, let's say, 70, well, it's the likelihood of obtaining 110.56 in our sample is 0, almost 0. Never 0 in a normal distribution, but very, very low probability. And the same for 80, the same even for 100. So the parameters, if only at 100 and let's say 7, 8, and there are some values above 0. So basically, to obtain a mean of 110.56, basically that has to come from a population in which the mean is in this range. Okay, so basically we transform the likelihood. So what I showed before is the likelihood. So we transform that into a posterior distribution. Remember that the likelihood, unlike the probability distribution, it doesn't integrate to 1, but the posterior distribution does integrate to 1. Now, what we need to do is to divide all the values of the likelihood that we obtain, weighted by the prior, but in this case it's 1, so it will be the same, and then obtain the marginal likelihood of the data. So when we divide all the values of the likelihood by the marginal likelihood of the data, we obtain a probability distribution, because now it adds to 1 if it is probability mass, so discrete values, and it integrates to 1 if we are talking about continuous values. So here we've got that distribution, which is the posterior distribution, and as you can see is very similar to the likelihood. It's almost the same. So the mean of this posterior distribution is 111, and the 95% confidence interval is from 109 to 113. So basically, in a Bayesian parameter estimation, we can be 95% confident that the mean of the population from which the sample we obtained came from is between 109 and 113. Okay, so third type of parameter estimation is by resampling. Again, we use R, and the way we do it is from the 400 scores. Remember, in resampling we don't use any theoretical distribution, we only use the values we obtain in our sample. So from those 400 scores we generate a new sample of 400 scores by replacement. So basically, if we had those 400 values, we take one randomly, we record that value, we put that value back to the 400, and we do that again. We draw a random value and we record that number, and we do that 400 times, and so we've got a new sample with scores which were resampled from our sample. And so we obtain the mean of that new sample, and then we do this process thousands of times, let's say 5,000 times, so we've got 5,000 means, and with these 5,000 means we generate a histogram, which is here, and the mean of this histogram is 110.56, which coincides with the mean of the sample, and the 95% confidence interval is between 109.4 and 111.7. Okay, so these are the three parameter estimation approaches. Basically, we estimate the mean of the population from which the sample came from, and we do it with a point estimate and with the interval estimate. Okay, so now model comparison. We are going to use two approaches as in previous videos. Maximum likelihood, and the Bayesian approach uses Bayes factors. Okay, so here we've got two researchers who have two competing theories about what values we should expect in this sample. Researcher 1 has the model 1, which predicts that the values in the population follow a normal distribution with mean 115 and standard deviation 15, and that's represented by this curve. And the researcher 2 has in mind model 2, which predicts that the values in the population follow a normal distribution with mean 125 and standard deviation is 50. So standard deviation is the same, but the mean is different, so that you can see in this distribution. So we obtained our data. It has a mean 110.56. Okay, is it more likely on the model 1 or on the model 2? Well, it's obviously closer to model 1 to the model 1, but is that much more closer in terms of likelihood or not? Well, that's what we are going to do. We are going to use maximum likelihood estimation or Bayesian approach to determine if what we obtain is much more likely on the model 1 than model 2, or just a little bit more likely. Okay, maximum likelihood, I did that with R. So basically we've got a distribution with a normal distribution with a mean of 115 in model 1 and standard deviation 15. So how likely is to observe, let's say, the value 80 in our let's say we obtain a value of 80. Well, how likely is that value of 80 in a distribution with mean 115 and standard deviation 15. So that's a probability. And we do that for all the 400 observed values. So we've got 400 likelihoods. And using the product rule of probability theory, in order to determine what's the probability of observing the 400 values we actually observed, we have to multiply them. But as I explained before, it's more manageable to work with log likelihood, so we take the logarithm of the likelihoods and then we add them, we don't multiply them. Okay, and we do that. We do the same for model 2, except that it's a different distribution. It's a mean with 125. So the value 80 will be much less likely in the distribution with mean 125 than in the distribution with 115. And let's say 130 will be much more likely under the distribution with mean 125 than the one with a mean of 115. So we did that for both models. The log likelihood for model 1 is minus 2333.3, and the log likelihood for model 2 is minus 2512. Deviance transform the negative values into positive by multiplying by minus 2, so we got 4666.6 deviance in model 1 and 5024 in model 2. And yeah, we use AIC to penalize for estimating parameters, but here we didn't estimate parameters. We fixed the parameters to 115 and 15 and 125 and 15 in both in the respective models. So we don't have, because we didn't estimate parameters, we don't have to penalize any of the models. So the AIC is the same as the deviance. The difference is 357 in favor of model 1. Remember that the lower AIC is better. So basically model 1 is overwhelmingly more likely under so the data is overwhelmingly more likely in the model 1 than under model 2. So it's not just a small difference. Okay, so now same idea but with base factors, and remember in maximum likelihood we've got one value which is we set the distribution to 115 mean and 15 standard deviation, or 125 and 5. In the Bayesian approach, what we do is to define a prior distribution for model 1 and a prior distribution for model 2. And the prior distribution for model 1 is a mean of 115 with standard deviation 5, and the normal distribution 125 with standard deviation 5. So we need to obtain the marginal likelihood in order to determine if the data is more likely under model 1 or under model 2. So again, I needed to use a algorithm called naive Monte Carlo in order to obtain the marginal likelihood. Here are the marginal likelihoods: 0.053257 for model 1, 0.01669 for model 2. So the base factor is the ratio of the marginal likelihoods, and you can see here that is 31.92. That means that the data is 31.92 times more likely under model 1 than under model 2, which agrees with the AIC in favor of model 1 that we found in the maximum likelihood approach. Okay, so now the third or category of approaches is the hypothesis testing, and we've got two approaches: NHST, null hypothesis statistical significance testing, and the Bayesian approach, which uses Bayes factors. Okay, so we've got JASP to do that. Basically, what we have to do is a one sample t-test, and we are going to compare the value of the mean we obtain in our sample to some test value. It could be 0. So if we can test whether the mean that we found is different than 0, but that wouldn't be very clever, because we know that it's impossible to have a mean of 0 in a population. So we may want to test again against a value that has some interest, for example 100, because in the general population the mean of IQ is 100. So we want to test whether our sample is different than the population or not. And so we test our sample against the test value 100. So let's do it with JASP now. So the file is already there, it's intelligence, so I'm not going to open it again. But now I have to change to t-test, and it's a one sample t-test because we only have one variable. So we put intelligence there, and we get this result. But basically that's as you can see, the t-test 189.9, but that's testing against the value 0. We want to test against the value 100, so we put 100 there and we press OK, and here you've got the result. The t-test is now 18, and it's the probability is less than 0.05, so it's a significant result, and we reject the null hypothesis. So that's the table I'm showing here. So that's the NHST approach. Very simple to do in JASP when it's when we can use a traditional test. And now for the Bayes factor approach, that's also very easy to do in JASP, because JASP specializes on doing Bayes factors. Okay, so we do the t-test of one sample, but the Bayesian alternative, and again we are going to test against the value 100. So return to JASP, t-test, but instead of going to one sample t-test, we go to Bayesian one sample t-test. Again we put intelligence, and the test value should be 100. Okay, so now we've got here the Bayes factor 3.391 e plus 50, so huge number in favor of the alternative model, where the null model is a spike on the value 100, and the alternative model is an alternative model has this prior here, which is using a Cauchy distribution with parameter scale 0.707. Basically the Cauchy is like a normal distribution. It's around 100, sorry, I need to change that to 100. Around the value, and I need to put intelligence there, sorry. So basically, again, the null model is a spike on the value 100, and the alternative model has a Cauchy distribution with scale 0.707, and that is like similar to a normal distribution around the value 100. And here is the base factor in favor of the alternative. We can get the prior and posterior, but it's not necessary because we're only interested in base factor here, but we can have this nice graph if we are interested in. Let me show you. Okay, so we've got this graph that tells us a bit more about the prior and posteriors. Now, what is probably confusing is that it's using effect size rather than the raw value. So basically, 0 would be equivalent to a value 100. And here we see that this is the posterior distribution. So basically, that means it's to the right of 100. And this is the prior distribution. So the prior distribution is around the value 100, but as I said, is a value 100 in this case would be effect size 0. Okay, so that finalizes the explanation of the base factor, and I now explained all the 7 approaches for analysis with one numerical variable.